Okay, this section is still chapter 9, section 3, but we're going to use those double angle identities to give what we call reduction formulas. Okay, so these reduction formulas, so whenever you have a trig function and it, like sine squared of theta, cosine squared of theta, we can usually deal with. But you're gonna run into trig functions where that power is greater than 2. And then we use these reduction formulas to be able to write those in terms of first powers. These reduction formulas come from our double angle formulas. I'll just show you one of them, and then I'll show you how to find one of them, and then we'll just give you the rest of them. So if you look at the cosine of 2 theta, okay, this is going to be our double angle formula for cosine. We have 1 minus 2 times the sine squared of theta. That's a double angle identity for cosine. Okay, if I solve this for the sine squared of theta, okay, I'm going to go cosine of 2 theta minus I want to add 2 sine squared of theta. That'll give me 1, okay? And remember, I wanted to solve for sine squared. Okay, so I am going to subtract this cosine of 2 theta. So I'm going to get 2 times the sine squared of theta equals 1 minus the cosine of 2 theta. And then if I just want the sine squared, I'm going to divide that by 2. So I'm going to get the sine squared of theta is 1 minus the cosine of 2 theta divided by 2. So that gives me my first reduction formula or reduction identity. Sine squared of theta is 1 minus the cosine of 2 theta divided by 2. Notice that this equality gets rid of this exponent, okay? And this works for any even exponent. The odd exponents, you have to do a little more work. You have to break them into 1 and then the even exponent. But then you can get rid of the exponents and write them in terms of powers of 1. Sine and tangent can be reduced accordingly. And then we have the 3 reduction identities. So this is the first reduction identity.
Sorry.
That's okay. Then you get the cosine squared of theta equals 1 plus the cosine of 2 theta divided by 2. And then your tangent is going to be the tangent squared of theta equals 1 minus the cosine of 2 theta divided by 1 plus the cosine of 2 theta. Okay, so those are your 3 reduction formulas that we can use. So again, just like we always do, we can use these to prove an identity. So we want to prove that the sine squared of 2 theta equals 1/2 the sine of 2 theta times 1 minus the cosine of 4 theta. Okay? Okay, so I'm actually going to work on the left side because we have formulas that reduce. So I'm just going to start working on the left-hand side. So I want the left-hand side to turn into this. Okay? So this was actually the sine to the 3rd. Sorry about that. Okay, so I'm going to say that this left-hand side is the sine of 2 theta times the sine squared of 2 theta. So that gives me 3 of them. Okay, so I'm still working on the left-hand side. I want to get it to eventually equal the right-hand side. Okay, so I'm going to apply my reduction formula, okay, to this right here, because I have a reduction formula for the sine squared of theta. So I'm going to say, I'm going to keep this guy. So sine of 2 theta equals, or I'm sorry, not equals, times, now I want the reduction formula for this, so sine squared of 2 theta is the same as 1 minus the cosine of 2 times whatever theta is, which in this case is 2 theta. And that is going to be divided by 2. Okay? So I'm still working on this, trying to make it equal that. So I'm going to simplify. So I'm going to get sine of 2 theta equals, or not equals, I'm sorry, I keep doing that. Sine of 2 theta times 1 minus the cosine of 4 theta. Just multiply these two together, divided by 2. Still doesn't look much like this, does it? But I can get pretty close if I kind of split this up. Okay, so remember we're multiplying all of these together. So this would be the same as the sine of 2 theta times 1 minus the cosine of 4 theta times 1/2. Because if we were multiplying all these together, we'd have, this is over 1, so we'd multiply the numerators together, multiply the denominators together, and that would all be the same thing. And so now it actually looks pretty much like it does here if I just reorganize them. So I can reorganize them into 1/2 sine of 2 theta, because all of this is multiplication, so it's commutative. And so now I have exactly what I started with. Okay, so let's go ahead for this one. You're going to do 9.3, and you're going to try numbers 39, and then 41 through 51 odd.